Quantum tunneling describes a phenomenon in physics where a quantum object teleports through a potential barrier that is classically insurmountable. It's like being locked up within seemingly inescapable walls, but then you randomly appear outside of them without using the tiniest bit of energy. This initially paradoxical phenomenon is paramount to the stability of our atoms and the existence of our universe. But a much more important question remains to be clarified. Are you able to perform this feat of tunneling? I mean, teleportation could really come in handy if you are in an awkward situation and you just want to disappear. Like last Monday. To answer that, let us first inspect an electron tunneling through a potential barrier. Why can he tunnel? What does he have that you don't? I mean, besides his attractiveness and high chances of finding a lifelong partner. That's right, he weighs less and has greater length. Size does matter after all, huh? According to De Broglie, every object can also be described as a wave whose wavelength is inversely proportional to the object's momentum. Naturally, an electron has a much larger wavelength than you because it has a much smaller mass. This brings us to the next very important question. Why does size matter? Let's look at how you and the electron would fare at tunneling through a barrier. Assuming you and the electron are perfect point masses, the problem scaled roughly down to the same size would look something like this. Here, the blue-colored wave represents the electron and the red one represents you. Intuitively, one would think that waves would stop there because the energy of you and the electron is too small to overcome the barrier. But that's not what's happening here. To do the physics, we need to use the one thing I and nature have in common. We only like smooth curves. So let me smooth those curves. Now, as you can see, the electron penetrates the barrier because of its greater wavelength, whereas you can't even reach halfway. Well, if we would be realistic, the picture would look something like this. As you can see, one wouldn't even notice that you penetrate the wall at all. Pathetic. Since the wave squared is a measure of the probability of the object being in that place, the electron has a high chance of being detected on the other side. You, on the other hand, will never be able to escape. But the electron also has its limits. The exact penetration depth is determined by the mass of the object and the difference between the object's energy and the height of the barrier. This means that the longer the distance you want to tunnel, the lighter the particle doing the tunneling has to be. This also answers the question of the video. Humans' quantum tunneling is like getting a physics degree without going insane. Not possible in the slightest way. That's why I started my second channel called History Speedrun. If I ever feel like I'm too mentally challenged by physics, I will start uploading mediocre history videos over there. See you on the other side. I can't sing. Sorry, I can't sing.